Hi, so in this lecture we're going to introduce the concept of the chi-square test of independence. Till now in the video series we've been talking about hypothesis tests, which are basically tests of means. So we are testing whether particular samples are coming from a specific population, or whether two different samples that we have are extracted from the same underlying population or not. In each of the tests that we've done till now, whether it's the one sample t-test, two sample t-test, or the analysis of variance, or the ANOVA test, the null hypothesis always has been that the means of the samples are the same, i.e. they are coming from the same underlying population. So for us to do a hypothesis test on means, the variable has to be a continuous or a ratio variable where we can calculate mean. But what happens if we want to test the distribution of nominal variables? When we have nominal variables, we can't do a test of means over there. In fact, the only measure of central tendency that we can use on nominal variables is the mode. And mode is a frequency calculation. So we are calculating which particular category of the nominal variable is occurring most often. So the chi-square test is also performed only on categorical variables. So it's a non-parametric test, i.e. we don't measure a parametric measurement like the mean or median. So we're going to test the frequency distribution of the variables over here. So it tests that how likely has any particular distribution arisen by chance from an expected or an unbiased distribution. And the specific distribution that we're going to test is the frequency distribution. In most cases, we test whether the contingency or the crosstab between two categoric variables is coming as per either the expected frequency table, or if these two variables would be independent of each other. The chi-square variant that we are going to concentrate in this lecture is also known as the Pearson's chi-square test, and more specifically it's the test of independence between two variables. The null hypothesis in this test that we are testing out, or we are checking, is that the two categoric variables that we have in a data set, they are independent of each other, i.e. Those two categoric variables do not have any relationship as such, or if I know the value of one of the variables, it cannot be used to predict the other. The alternative hypothesis is that these two variables are not independent of each other, they have some sort of relationship, and if I know the value of one, I can make a guess, or I can predict the value of the other, which is better than a random prediction. How we actually do this test of independence between two variables is we compare the actual crosstab frequency of these two variables with the expected crosstab frequency if these variables had no impact on each other. So a crosstab is always the frequency distribution or the frequency interaction between these two variables. The greater the deviation between actual and expected frequencies, less likely is the null hypothesis to be true. Now I'm going to go about solving an example of a chi-square test in this video to give you a hands-on experience. So while this text or the theory behind it may not come out very clearly if we're just looking at the slide. So in the next few slides, I'm going to take you through an example. We're going to calculate a crosstab. We're going to check whether this one variable impacts the other and imply a chi-square test on it. In the chi-square test, the specific calculation of the chi-square is based on observed and expected frequencies for each cell of the crosstab. The formula that we apply is observed minus expected whole square divided by expected. So this is the chi-square formula, and the summation over here, the sigma sign, is simply the, for each cell we calculate the observed minus expected whole square divided by expected. We calculate this for each cell in the crosstab, and then we add this value up for all the crosstabs that we have to get the total sum, which is our chi-square value. And that chi-square value is again a cumulative distribution, just like the f-test that we have. So we refer to the appropriate chi-square table and convert that chi-square value into a p-value, and then figure out whether, based on the p-value, for any particular hypothesis test, we're always looking at the p-value, and we figure out whether we need to accept or reject the null hypothesis. Now I'm going to move into a practical example of the chi-square test, and it will become very clear to you how the chi-square test actually works in the background and how we can actually go about using this. So in this example, we're going to take a school distribution example. So assuming we have a school of about 500 students, and each of the student is allotted to one of four houses or groups in the school for, let's say, competition purposes. The school houses are red, blue, green and yellow, and every student is classified by gender as well as the house of the school. So the hypothetical data set that we have, we've got two columns over there for each student. One column records the gender, the other column records the house allotment of the school. Now both of these columns would be classified as nominal variables. So there's no such thing as average gender or average school of the student, but we can find out the frequency distribution of both the variables. And if we generate a crosstab between these two variables, this is the crosstab that we will get. Males and females on one side and the house allotment on the other. Now what we want to test over here is if there is any gender discrimination in the house assignment of students. I.e., is there a house which is discriminating by gender, or is this the distribution that we can expect to get if there is no gender discrimination at all? So in this particular case, the null hypothesis is going to be that the two variables, the gender and house allotment, are completely independent of each other, or that there is no gender discrimination. These two variables have got nothing to do with each other. The alternative is that yes, gender does impact the house allotment, and there might be gender discrimination when we want to test it at a particular level of alpha. So we've got two variables, but if you look at it, we cannot apply any of the previous tests over here. So you can't do an ANOVA or a t-test because there is no such thing as average gender or average school, or sorry, the average house that we can test over here. We need to do a frequency based hypothesis test, and this is where a chi-square test can come in. So I'm going to apply the chi-square test over here. And as mentioned in the previous slide, the chi-square test compares the observed frequency t. So these are the observed frequencies. For each of the cell, these are the frequencies or the number of observations. So this is nothing, this is not the mean, median, etc. This is simply the number of students which are classified as male and in the house, in red house. Similarly, the number of students which are female in blue house and so on. So this is the frequency distribution, and for each cell, this is the observed frequency. Now the chi-square formula uses observed minus expected frequency whole square divided by expected frequency for each of the cells. So now lies the first problem that we have to solve. What is the expected frequency? So we don't get the expected frequency automatically. We only get the observed frequency when we build a crosstab. So I'm going to show you how to generate the expected frequency. So I'm going to copy this over here, and we get the observed frequency. Let's create another table. I'm going to call it the expected frequency, and let's delete this. We will populate it with the expected frequency. Now the null hypothesis that we are testing is that gender has got nothing to do with the house distribution. There is no gender discrimination. So what we can do is we can calculate what would be the expected distribution in each of the cells if there was no gender discrimination at all. How do we calculate that? So first thing first is I'm going to calculate what is the total number of males and total number of females in the school. So we get 239 males, we get 261 females, and a sum total of 500 students. And I'm going to calculate how many students are there in each house. So we get 165 students in red house, 125 students in blue house, 100 students in green house, and 110 students in yellow house. So now looking at this, can we figure out for these 165 students what would be the number of males and females? Now if you were to say that if there were no discrimination, the distribution would be 50-50, right? But that would be correct if in fact we had equal number of males and equal number of females in the school. But we don't have that. As you can clearly see, we've got more females than males. So if there were no gender discrimination, these 165 students would be classified in the same ratio of males and females as in the overall school. So if I look at this, what percentage of the students are males and what percent of students are females in this school? So let's calculate the percentage. So we see that about 47.8% of the students are males, 52.2% of the students are females in this school. So in Red House, which has got 165 students, we can expect 47.8% to be males, 52% to be females. So I'm going to do that. So I'm going to say in Red House, which is 165, the percentage of males is going to be 165 into 47.8. So the expected frequency or expected number of males in the house would be 78.9. Now frequency doesn't work in decimals, but in this calculation of observed and expected frequency, we can let it be in. It doesn't matter if we get approximates or decimals, etc., because the chi-square test can handle that. The number of females that can be expected in the house is again the total number of students in the house multiplied by the percentage over there. So 52.2 of the 165 students are expected to be females. So we get the total number of males and females expected, and the total sum is 165. So this is the expected frequency distribution if there were no discriminations. If gender is not being discriminated in the house allotment, in Red House you would expect 78.9 males and 86.1. So expected is 78.9, observed is 87 and 78. So is there any distribution? Is there any bias? So looking at this, you can see that there is a bias. There are more males than expected in this house. We expected 78.9 males or 79 males, but these have 87 males. And similarly, females are 78, whereas expected is 86. So more male preponderance in the Red House than you would expect. But is this deviation significant? And not only this, we have to test it for each of the cells in this crosstab. So I'm going to calculate the observed and the expected frequency for each of the tabs. For Blue House, we multiply 125 into the percentage of males, and for the females again 125 into the percentage of females. Did I do something wrong? Yeah, I got a minus sign over here. Right. Similarly, let's do it for greenhouse. So green into percentage of males. Again, I'm sorry, I multiplied this with the wrong. So it has to be the column total 100 multiplied by 47.8. So we should get 47.8 there. And similarly, it should be 100 multiplied by 52.2. For yellow, again, we look at the yellow column total, multiply it with the percentage of males, and again the column total multiplied with the percentage of females. So here we have it. We have the observed frequency matrix that we have got in our particular data set. We've got the expected frequency matrix if there was no particular gender discrimination. If gender and house were actually independent of each other, this is the expected frequency distribution that we get. Now we want to test is that whether the observed frequency distribution is significantly different from the expected. And by significantly, we are saying that can the observed distribution arise out of chance or due to sampling distribution from the expected? Is this deviation between observed and expected significant or not? And this, so we have the chi-square formula applied, and we have the expected frequency table if there was no discrimination. So we've already calculated the expected frequency table by using the formula given over here. A quick way of again capturing the expected frequency if we don't want to use percentages in each is a very neat little formula. So if you look at this particular formula, what it's essentially saying is it's multiplying the column total into the percentage of the row total. So in other words, if I calculate the summation of the full row total in this cell, which is for greenhouse for females, this is the row, so I calculate the row total. I multiply this with the column total. So this is the column total of all students in greenhouse, and then I divide this by the full total of the students in this school, which is 500, or I take the full total like this, and I should get 52.2. So this is the expected frequency for greenhouse for females. So similarly, I want to calculate the expected frequency for males in blue house. I again look at the row total. So this is the row total. Multiply this with the column total. The column total is over here, and I divide this whole by the summation of 500, or all the observations or the total number of students, and I get 59.75. So this formula is essentially doing the same thing which the formula over here is doing. And it's very simple. I add up the row, I add up the total in the row, I add up the total in the column, and for each cell it's simply the row total into the column total for that cell divided by the total number of observations, and I can calculate the expected frequency in any given crosstab. So this will work in 2 by 2, 3 by 3, 4 by 4, 4 by 2, 4 by 3, any x into y crosstabs that we can build. So we've got the observed frequency, we've got the expected frequency. The chi-square formula is the summation of observed minus expected whole square divided by expected for each of the cells. So I'm going to calculate the squared deviance between each of the cells and add it up. So let's calculate this as the chi-square deviance. So I'm going to calculate the chi-square deviance for each of the cells. The formula is simple. I am going to take the observed minus expected frequency. So this is observed minus expected frequency. Raise it to power 2. So I'm using the raised to power 2 sign over here. So the observed minus expected whole square. Now I need to divide this by the expected frequency. So this is the expected frequency. So this gives me the chi-square deviance for this particular cell over here, and I can apply this formula throughout to get the chi-square deviance for each of the cells over here. And then the chi-square formula says the summation. So the total chi-square deviance which is coming in my observed versus expected frequency table is 3.80. The formula, so the chi-square test or the chi-square value is coming out to be 3.80. So I get 3.80. Now, is this value significant, or now we can look at the chi-square table and figure out whether this value lies in the acceptance region or the rejection region for this particular distribution. So this is exactly the same when we look at either the t-test or the f-test. So one note of caution over here, since the chi-square formula is using the raised to power sign, it doesn't matter whether you do observed minus expected or expected minus observed, the chi-square value can never be negative. It will always be positive. So the value of chi-square can range from 0. If the observed frequency and expected frequency are exactly the same, then the total chi-square summation will be 0. And the higher end, it can go up to infinity. So as the distribution looks over here, so if you look at the distribution, the closer it is to 0, the higher is the probability. The higher does the chi-square value go, the lower does the area under the curve start going down. So if I want to draw, so I'm going to just draw out the chi-square distribution. So again, it's a right-handed distribution. It does not have any negative values. So how do we actually figure out whether our chi-square value that we've generated is significant or not, or is in the acceptance region or rejection region? So let's have a look at the chi-square distribution. So let's say we've got the chi-square value on x-axis and we've got the probability on y. So this is the chi-square value over here. So let me make a better looking chi-square. So chi-square is sort of a x, so it's a Greek symbol over here, and it's a continuous distribution. So it goes from 0 to infinity, and it goes something like this. Now it depends on the degrees of freedom for each of the chi-square values. So I'll talk about degrees of freedom. So depending on the degree of freedom, we get slightly different chi-square tables for each of the degrees of freedom. Now let's say my chi-square value comes out to be 3.8, right? Is this t, and at alpha equal to 0.05, let's assume the chi-square critical is over here. So this is chi critical. Therefore, the region beyond this, so this is the region over here which goes all the way till infinity. So the area of this region is 5% or 0.05. If I put my alpha equal to 0.01, if the alpha value is 0.01, then this chi-square actually moves over here. So this is chi-square critical at 0.05. Let's say at 0.01, I'll have another chi-square critical, which is over here at 0.01, and so on. So we need to figure out if this value or chi-square which I've calculated lies in the acceptance region or does it lie in the rejection region. I can simply compare this value with the critical value of chi-square for the appropriate degrees of freedom and figure out whether I will accept the null or reject the null. So looking at this particular problem that we have, I need to figure out first is the appropriate degrees of freedom. The degrees of freedom is calculated based on the crosstab. It is row minus 1 into column minus 1. That gives us the total degrees of freedom. So I have got two rows over here in this data set. So this is my crosstab. So two rows. So 2 minus 1 gives me 1. Column minus 1. So I've got 1, 2, 3, 4. 4 columns minus 1. So it gives me 3. So essentially 3 into 1. So I have 3 degrees of freedom in this crosstab. So I need to look at the chi-square table for 3 degrees of freedom. So over here we have got an approximate chi-square table. So we see that for alpha equal to 0.05 at 1 degree of freedom, the chi-square critical value is 3.84. For 2 degrees of freedom, it's 5.99. For 3 degrees of freedom, it's 7.82. So this is not the full chi-square table. This only gives us the critical value at 5% level, at 1% level, and at 0.1% level at different degrees of freedom depending on how big a crosstab is. I see for 3 degrees of freedom, the critical values of chi-square at 5% is 7.82. So if I look at the diagram which I have to draw, so let's say this is my chi-square value, this is the chi-square distribution. At alpha equal to 0.05, the chi-square critical value is 7.82. So this is 7.82, and this shaded region now is 5%. The chi-square value that I have calculated based on the previous slide is 3.8. So if I look at 3.8, it lies somewhere over here. So 3.8 very clearly lies in the acceptance region. It is lower than the critical value over here at 5%. When I go to 1%, the acceptance region value even increases further. So at 1% level, the critical value is not here, it lies somewhere over here. So, and if I go even further, then it goes up to 16.27. We're going to test this at 5%. At 5%, the critical value lies over here. The chi-square value that we've calculated clearly lies towards the left of that, so it's in the acceptance region. Therefore, in this particular example, discard this. Yeah, so for this particular example, the null hypothesis is retained, i.e., there is no gender discrimination in the data set that we have. So in this particular school example, there happens to be no gender discrimination between the house distribution and this deviation that we are getting. So we are observing this is the gender distribution. This should have been the gender distribution. So obviously there is a deviation, but this deviation is not statistically significant at 5% level. Therefore, we cannot accuse any particular house of or this particular school of discriminating by gender when it comes to house allotment. So this school is not practicing any gender discrimination which can be proved at a significance level of 5% or even at 1%. If we start increasing the value of alpha to, let's say, 10% or 15%, then the hypothesis might change. But again, we can't change the alpha post facto. Once we look at the test, you can't go back and say, oh, at 5% it's not coming significant. Let's try something else. Let's try an alpha of 20%. No, it doesn't work that way. You need to be figuring out the alpha and the type 1 and type 2 errors well before in advance. So looking at this, at a 5% level, there is no gender discrimination, and this is the power of the chi-square test over here. We can actually compare the distributions across two nominal variables in a crosstab and figure out whether two variables are independent of each other or not. And this was an example of a chi-square test, and I'm going to show you how to do a chi-square test on SAS. The procedure is simple. We use it using an extension to the PROC FREQ, procedure itself. So when we do proc freq data equal to data set name and tables variable 1 into variable 2, we actually end up creating a crosstab. We just need to add a option over there /CHISQ or the chi-square and run it. It automatically runs a chi-square test on the crosstab that we generate. A caution that we need to make sure is that the two variables that we run over here are both nominal variables. The chi-square test is very powerful at 2 or 3 in a crosstab which goes 2 or 3 to 4 columns and rows. It should not be used where your crosstab is very big. If you've got like a 10 by 20 or a 20 by 20 crosstab, chi-square test is not appropriate for that. So anything more than 5 by 5 is actually not good to use. The other caution that we need to use is chi-square test is not accurate in frequencies. Any cell observed or expected goes below 10. So if I look at this, so we've got a healthy chi-square distribution over here. We don't see any particular cell either in observed or expected which is going less than 10. So it's fine. But when you start building up big crosstabs, there will be cells which have values which go less than 10 or less than 5, and that's not appropriate. So chi-square test, the power of that chi-square test starts to taper off over there. So these were the two cautions that we need to make sure. So one caution, it should only be used between nominal variables. Two, we shouldn't have too many cells in our crosstab, and make sure none of the cells has a frequency less than 10. So in our next video, we're going to talk about a few example exercises on HSB2 dataset. So I'll run all of these examples on SAS, SPSS, and Statistica, and on then ask the students to run these tests on the telecom data on their own. So I'll see you in the next video.